Before we start the panel discussion, let me try to answer the questions from the audience. And there's one from Zhou Han. What? Where was that? Yeah, he's asking Patrick, what is the main cause for the surface activity of asteroids?
Yeah, that's a very interesting question. I sent a response by writing, but so we don't really know. There are different possibilities. For Bennu, if we talk about Bennu, there are different scenarios. We cannot discriminate yet. So one is the fact that because it rotates about 4 hours and it has hydrated minerals, it's possible that thermal desiccation, thermal dehydration is the cause of this activity. Another possibility would just be micrometeorite impact, because when you look at the frequency of these impacts, they are consistent with the frequency of the activity. However, if this is micrometeorite impact, they should also occur on all asteroids, and all asteroids should be active. And in fact, it may be true. The only thing, and we checked that, is that all the other missions did not have the capability to detect this kind of activity, because these are very small particles. So we cannot discriminate yet between these different scenarios. And there are also other asteroids that are active in the asteroid belt. And there again, there are different possibilities. One is simply a breakup due to the Yorp spin-up that could generate the pattern that we see. The other one is again the fact that some of them now we know contain hydrogen minerals and also ice inside and even outside for Ceres and Themis. And maybe when they experience an impact and then the ice vaporizes, it gives pressure and therefore you get the activity, sort of like what we have on comets. So the bottom line that we don't really know. There are different possibilities. Whether these different possibilities all occur is also possible, or whether there is one scenario that dominates is also possible, but we need more observation to understand that.
All right, thank you for your answer. And I see you said just now you put your answer written on the Zoom platform, which is great. And before you guys ask each other question, I will shoot one quick question to you guys. I really think it's a good panel connecting both science and technology together. And there's a lot of science point of view and a lot of engineering stuff. What do you think the bottleneck for both science and technology for space mining? Is there any bottleneck technology that still need to be developed in a hard way? Yeah, go ahead.
Well, if I may, so I basically would have that question to my co-panelists for specific questions, but I can ask that later. I basically think we do not have technical bottlenecks. I think the bottleneck is, as Amara Grabs described it, the business case for industry to go there is a long shot. Then for the agencies, it's also a long shot, and you need to hedge your bets. And then it's the ambiguity if things will work. Yeah, I think if you can specifically narrow down what kind of technologies need to be brought to maturity, the scientists and engineers can deliver. But it's, I think, the big gap between what we know now and what we need to bring to fruition technology-wise to be safe such far away. That's the biggest problem. So that I have no answer to that. So there are more people on the panel who have thought about that. But you either fix everything and say we go to the moon or to a specific asteroid no matter what, and then everything is settled, or you leave it open and you go science and technology first and missions later.
I can add if you want, since it's a lively discussion. I think there are various difficulties, and of course it depends again on the business case, how much risk you are able to take. because the main problem that we have so far is that until we go on site, we have no way to determine the mechanical properties of the objects. For the composition, we have spectra. It doesn't tell us all, but at least you can sometime identify whether you have hydrated minerals, if you want hydrated minerals. And with all these missions that are coming, we'll be able to have more ground truth about the remote observation from the Earth and the in situ observation. So for this, I think we learn a lot and will be more or less okay. The only issue is that if you have to design a tool that works, it's complicated when you don't have any a priori information on the mechanical properties. And you can see with these science missions, we use a touch and go approach because we take a minimal risk, and that only allows you to get grams of material, which is largely enough for the superb cosmochemist community who is able with even micrometer size samples to tell us all. But when you want to mine and do something with your material, maybe you need more. In that case, you start to think about landing, but landing may mean anchoring because you want to stay on the surface on the low gravity. Anchoring means designing your anchors so that they can couple with the surface. We saw with the Rosetta mission, it didn't work for Philae, unfortunately, because the surface was harder than we expected. So that, I think, is the most difficult part of it, is to have a way to design a tool that is flexible enough to couple with the various kind of surfaces in the low gravity environment. And also all the close proximity operations that now we better understand in some agencies, but for a private company, they also need to gain experience in that. But that's easier because you can gain the experience. So one thing to think about is how can I design a mission that interacts safely with the surface to do business without a priori knowledge? Or can I have a business plan that allows me to get a precursor mission that tells us about these properties with the complexity of the celestial mechanics that is such that when you go one time, the second time, the body is elsewhere. So of course, things are feasible, but again, these are the things to consider, the design of the tools, how you want to extract, and how much information you need a priori. If you need not much information, that's fine. But this, I think, is the most problematic thing.
Well, thank you.
Just to add to what my fellow panelists are saying, what I pick up is I think this kind of commercial initiative, either is astro mining or looking at the moon. From my perspective as a roboticist, I find there's a requirement of in terms of paradigm shift of the design philosophy. So because because you're looking at a commercial initiative, you want to make money out of it. So therefore, it has to be a sustainable development mission. It's very different from exploratory mission or the scientific mission that we've been very used to design things for. From an engineering point of view, I do agree with Matthias. We can overcome it, but it does require a change of design philosophy from what I observe, because you need something that can last, can sustain there. And it does require design, the way that we design it will be principally different, from your perspective. I think as a commercial, mission, you want something to be there, long-lasting, repeatable, modular. It can be serviced, right? You don't want to just launch something, it only have a very limited lifetime. It's not working, it's fine, you just resign something. No, you have to have something more sustainable. I think it does require paradigm shift in the actual design. It's doable, but it's not necessarily how we do things right now and the way we approach things right now. So that's what I say being a challenge, not necessarily a bottleneck. I think I agree, you can overcome it. You just need, people, everybody in that supply chain to all change their thinking. That includes the business, the sort of research, who does the low TRL stuff for you, and also the government. I think you need to look at legislations, also regulatory bodies. Also, people probably have to come up with new standards that can meet, your expectation of sustainability, for this to be a sustainable business. So all those stakeholders has to be there to make this happen.
Yeah, I would say I agree with that. I'm super optimistic that innovative approaches and the one that usually in classical agencies we don't have because there is a different spirit can allow to solve problems. So that's where, and I would say, so if you look at the moon and Mars, these are two bodies, and here we have a better understanding. And with asteroids, what you need in innovative approach is flexibility, because they have advantages. They have a very diverse composition, so you can really have access to very different kind of materials. But they have the complexity that their size is very different from one to the other. Some rotate very fast. And so you have to take into account a much larger number of parameters. Some are unknown in order to design a mission that, as you said, should work in all cases. And of course, with artificial intelligence, etc., maybe you have more flexibility. So I would say, I'm not saying a very negative message. On the contrary, I think that knowing in advance the complexity allows you to find solutions. I'm sure with all the new advances in technology, we can find solutions. And therefore, in that case, you can use the advantage, if you are looking to small bodies, to the incredible diversity in composition, trajectories. I mean, there are a lot of things you can do knowing that in advance. So, but I agree, it has to have needs to be a paradigm shift in the approach of the problem. It's very different to do a science mission and a
maybe adding a technical perspective to that aspect, Patrick. I thought to involve Amara, but I'm not sure if she's here. If you do plans for lunar resource utilization, first thing is prospecting, if there is anything there, and there's a big mining distinction between resources and reserves. So there's no big cavities. Hi, Amara. There's no big cavities of gold and platinum that you just need to dig out. Yeah, it's rather more spread out to the absence of geotechnical and tectonic processes on the moon. It is possibly a fruitless issue to find anything as precious as a gold mine on the moon. Now, to turn an argument of Amara around, once you go to the moon, you're there, you need an infrastructure to do prospecting. And if you find something, you know where you found it. So what would be the equivalent of finding the most promising asteroids? Yeah, because you need you would say you need individual missions. That's a goal. Yeah, that's a large upfront investment. Or do you have any way of doing, let's say, remote sensing, prospecting? Imagine, well, a weird thought. You go to the asteroid belt and then you fly by 1,000 objects. You have learned what red and blue and other spectroscopic issues mean. Yeah, that is, let's say, what I mean by light and grain interaction. What does that mean? What does that tell you? What can you learn from that, at least with a higher probability than just shrugging your shoulders? So how would you narrow down where you actually go and land or what you capture? Is there some asteroid prospecting possible? Maybe to both of you, Amara and Patrick.
This was a discussion at the end of the 2018 ASME where we were discussing different mission scenarios. And I think that the miners build in the risk of failure so that they can make a decision based on minimal information. Like we, for composition, looked at data mining WISE and big data sets in spectrophotometry in order to get a basic set of composition information and which bodies are available. So it seemed, at least 3 years ago, that that was possible to make some decisions after discovery. And it was enough to start building out a mission. Now we have more technology available for propulsion that I think can extend a mission so you can start to do asteroid hopping. So that mission that I was describing before is from your institute, it's from DLR. There was a fantastic presentation about going from one asteroid to another. And I can send to you that presentation if you want, because I know your institute is large. It was really fascinating to think about how you could go for years at a time, just hopping from one asteroid to another. So anyway, that's my short say. Probably let's see what Patrick has.
No, I mean, I agree. It also depends on what you are looking for. If you are just looking
Right.
at, water, or if you are interested in much wider range of minerals, then that's a little different. So from spectral observations and data mining, effectively, you can better understand statistically where are the interesting bodies in terms of, for instance, hydrated minerals. We have some bands in spectra which are characteristic. Now, if you are interested, more ambitious, I would say, then effectively having missions that go through the belt and do some flybys, allowing us to get also a statistics with more detailed information, because the interesting thing is that we realize with some cases that these bodies turn out to be much less homogeneous when you go at small scale than what we see from the spectra. I mean, Amara does know very well this example of 2008 CC3, which was a 4-meter size asteroid that was discovered 20 hours before impacting the Earth. And the spectrum was telling us that you should have, basically a primitive composition, and the 600 fragments were collected in Sudan from it, and they have a very wide range of lithologies, and that you cannot see from the spectra. So if you are just interested in one mineral which has a characteristic band, then with the ground-based observations and data analysis, innovative one, you can certainly do something which is already good, I would say. Then, of course, if you want to do more, you can do some flybys mission that tell you more about it. And I think both are complementary. I would go for both of them.
Yeah,
So if I may.
go ahead.
So I had another question to Yang Gao, also triggered admittedly by discussions we have at DLR, which has different institutes and other divisions. How secure do you feel on the soil in terms of, you have a rover, you have all the robotics components, and how well do you know the soil? And in general, is the modeling part that you do for that reliable, or would you say all the rovers on Mars show by getting stuck at some time that there's more stuff to be done? And would you rather see the problem on the modeling side, or would you lean toward doing better diagnostics to on the side find out if the soil is weaker or more bearable?
Yes, thanks, Matthias, for the question. It's a very practical question. I think the truth is, the honest truth is, as I think Patrick already said repeatedly in his talk, we have to anticipate uncertainties on those sites, even with repetitive missions, what you find is you will always have novel features that you've not encountered before. So my design philosophy always tend to be, you have to preempt some of the uncertainties. And therefore, what that means is in the design itself, you need to, particularly when it comes to locomotion design, mechanism design, you have to encounter a range of operational parameters, and knowing how much you can do with certain designs, and possibly, in my personal view, even for the mechanism, we need to look at reconfigurable approach. So meaning you have to design space robots that can reconfigure its mechanism for different potential scenarios. Take drilling or something as example. In my view, you need to have a portfolio of different tools when it comes to assembling and drilling on your spacecraft to really be able to address different scenarios. But equally importantly, I think what you said, this other aspect, which is in situ sensing and diagnostics, that's equally important in my view, because if you want to fully achieve reconfigurability with the hardware, you need to have a proper sensing ability to do that, to make that judgment. So both are very important. But I think goes back to my point earlier. I think there has to be a paradigm shift in the design of the robotic or engineering solution here for this kind of commercial initiative, because they are really looking at something has to be very sustainable for their business to be valid. So therefore, we have to go beyond the classical engineering approach with existing missions. So for example, things like this reconfigurability, self-verification, as I was saying in my, I think, second last slide, is really trying to point out the fact we have to have a more sustainable approach in our engineering design moving forward for this kind of commercial initiative. Otherwise, I don't think they can justify this from a kind of commercial motivation point of view. It's just not sustainable. So yeah, I personally think it needs to be far more reconfigurable designs in the future. It has to be self-verifiable as well, which I think both are not something we are doing enough with existing missions, which rightfully, I'm not complaining, I'm saying rightfully, with the constraint we have, budgetary and time and everything, we are doing what we can as the right thing to do. But for this kind of commercial initiative, I'm afraid they have to take a different approach if they want it to be sustainable. Yeah, but it's yeah, that's my view. Hope it makes sense.
I can, if you want, I can. Yeah, I think you are very right. And that's possibly difficult for a business plan if you want to have something which can be reconfigurable. There is another possible thought, which is that if we, because we are still in the thing is that we are still in the process of trying to understand these bodies, and I'm talking about still about small bodies, because for the moon it's just one kind of gravity, for Mars also, and therefore maybe easier. But for asteroids, we are still trying to understand what they are, how they behave, etc. So the optimistic view is that, and that seems to work at least for Yugu and Bennu, different types have different properties, but within the same time, they basically behave the same. That would be the best optimistic view. And maybe possible, because we see Rigu and Bennu, they are same type and they behave on their soil like cohesionless bodies. So if that's true, that allows you to already make the design of an instrument that, even though it can be reconfigurable, you may put more weight to one kind of tool that works for this kind of soil. And therefore, with the next mission, maybe we'll see that S-type bodies behave differently and all the same, and therefore you can also make a tool more appropriate for this kind of soil. So maybe there is a simpler way if we find that there is a common characteristics among different types. And the moon also, I mean, I think we know, I mean, it's made of very fine regolith. And by learning, and that's where I think the modeling is useful, because that's what we're doing. I mean, with this granular material modeling, we do some experiments in low gravity to try to validate them. But of course, low gravity, even parabolic flight are very short. A drop tower also is very short. And hopefully with all these missions, scientific missions for now going on, we learn better whether our modeling needs to be improved and how to adapt it. And so this back and forth interaction between the modelers and the engineers and the science knowledge of these bodies can maybe optimize the design of a tool that is appropriate per types of asteroid if they behave the same in each type. But of course, the thing is that, of course, the miners, they want to go fast in the business. And I think we are still one step before, where we need better understanding, which maybe will simplify everything at the end if we find some common characteristics within each type.
Another thing I want to say is which is very interesting. Well, I'm just listening to Patrick and Matthias, is that with this kind of asteroid mining initiatives, I always wonder the plans of the human involvement, because in the current mission, we mostly they are done robotically, but they're also remote operation, as you guys know, for example, with the space station, etc. I always wondered, because I guess I have a very limited knowledge of the actual body itself, like the asteroid, because I'm not a planetary scientist. But I always wondered, what is our envisaged operational scenario for this kind of mission? Is that mostly autonomous robotic operation, do we think, or do we think it has to be some kind of human operating the loop at some key stages? So I always wondered, what are the envisaged operational scenario for this kind of commercial missions? I don't know who have the answer, or is that still under debate? Because that would be very interesting.
It sounds to me like this is a question to our host and a question about the business plan of Origin Space.
I agree.
So do you fly there with Spaceship Enterprise and have a remote controlled deployment of a mining tool? Is that your vision?
Yeah, not really, but Mengsu can make a comment on this, I guess.
I think we are trying to, actually I had a related question. So before we can reduce the cost and make cost-effective missions, many missions to many asteroids at the same time, and help to fastly build up our modeling asteroids, how can we define the minimal version to provide to get prepared for the next really mining level activities? So we kind of hesitate to move on to get a mature design of the cost-effective mission. So that's why we think many things, but when we really do missions, we do telescopes, we do net capture, because these things are kind of within the horizon that we can achieve with effective current budget. So there is a gap between our what can and what we hope to do, but we don't really know what the most cost-effective thing, like a minimum version or like a cheaper Hera, or what should be the cost-effective mission for the next thing in the roadmap.
I can say something about that too, is the fact that so far humans had to be there because all the what we saw when we arrived at each target was totally different than what we expected. So there were new decisions to be taken. But what I saw is that machine learning is a super effective tool, and maybe little by little we can decrease the amount of interaction of human decisions for operations. Because for instance, with those iris rays, they basically the spacecraft made a catalog of images that allowed it by itself to detect the dangerous zones and therefore land safely. So if you know this in advance, so we didn't know in advance that there were so many boulders. So that's why it was not used initially and we had to decide to use it. But if you know in advance that, okay, we don't know what's going to find and maybe the surface is rougher than we expect, initially you can decide that you will use these kind of tech tools to make a safe landing. And in that case, you need less human decisions. So I think the more we will learn about these bodies, maybe that will decrease the uncertainties and therefore the human in the loop, especially with these new tools with machine learning and artificial intelligence. But before being there, I think we, and again, and also, sorry, if you have a precursor mission, that's even better, because then you have a full understanding and you can prepare initially everything automatically for the next real interacting approach. So there are different ways maybe to decrease the human decision in the loop, but so far, unfortunately or not, human had to decide something on site.
Yeah, that was my question. What do you think the suitable precursor mission would be?
A suitable precursor mission would be a mission that gives you images of the roughness of the surface so that you can decide on the landing accuracy you need. Well, of course, if you are interested in composition and you need more information with a spectrometer. And I would say you need something that touches the surface, just to have a sense, even not fully in detail, if you want to do it cheap, but have a sense of how it behaves. And I would say the simplest thing would be a sphere with an accelerometer. And then you see how it bounces, and that gives you already something about how the surface behaves, whether it's hard or soft. A sphere is good because otherwise you never know whether the geometry of what you use may have an effect on the bouncing properties. So I would say that would be the simplest. It's not necessarily simple, but the thing to do is that at least so that you know again whether you need a very high landing accuracy, so more expensive, or whether you're okay with a nominal one, and that gives you a sense of what kind of tool you can use. I would say that's the minimum. With the complexity that when you launch your mission to your target,
so
maybe it's reachable.
That's a Hera-like mission, right?
No, it doesn't have to. Well, I mean, of course, if you can afford an Hera-like mission, it's great. You have 2 CubeSats, etc. But I would say not necessarily. Because Hera has 2 CubeSats, a low frequency radar for internal structure, you may not need this kind of level of knowledge. I would say just images with A spectrometer is even better unless you already have enough information from the ground. And as I said, just a small, sphere impacting with an accelerometer, like the sort of the Minervas that were on Hayabusa 2. It's not super expensive, and it gives you already something which is very, I mean, it's not only better than nothing, it's, I think, very, very interesting. And make it safer, your spacecraft afterwards, with less human decision. So it doesn't have to be as complex as Hera. But one complexity, however, is the celestial mechanics. Is that, I mean, as you know, you may have a launch window which is favorable for the precursor mission, and then you lose you have to wait a long time before having another appropriate cheap launch window for the mining mission. So that's another parameter to take into account. And that's why, sorry, I'm talking a lot, but that's why if we can have a higher inventory of these bodies at small sizes, obviously small sizes are more numerous, and therefore statistically you have better chance to find a easily reachable object. But small mean also maybe sometime rotating faster, lower gravity, so more complexity. So it needs some thought, but I think there should be a sweet spot with all these parameters that will make it feasible and optimized given the money and everything to take into account.
Okay. Thanks, Patrick. Thanks for all the panelists. It's almost time to conclude this panel. How about everyone just give one last statement of what they think about the space resources future in the point of view of science and technology? Yeah. Yeah, Professor. Yeah, Spiro, just, yeah, go ahead.
Should I start because I was the first in that submission? So I'm truly excited to go places. I find interesting that from me as a microgravity ISS space station person, the lunar, Martian, and asteroid people all have different agendas, problems. I would recommend, and I feel very motivated, both ESA, NASA, and the Chinese agencies should have a look in combining what we can learn near term on the space stations from whatever technology we feel relevant. Certainly, I love grains. I'm privileged to play with sand on space stations. That's what I tell my 5-year-old son, and he thinks I'm getting work done for free. I think we should truly look at the interfaces of the communities to speed up what can easily be done and facilitates precursor missions, if that is truly satellites or is sort of a mock-up that not every planetary person would call a precursor. So I would congratulate Origin Space for organizing that session, congratulate people doing missions in that direction, because we probably look for exciting times for the time ahead for ourselves and our children.
Thank you. Yeah,
Okay,
Patrick, yeah, go ahead.
I go for it. So first, I thank you for having invited me. I think it's very interesting, and I would say, like I think Jean-Jacques Dordain, the former director of the European Space Agency, said, space mining is very important, and we need to get prepared before we actually need it. So it's very, it's great that there were these initiatives, and the Origin Space, of course, is super active in that, and I think this is great. And I'm very hopeful that things will come through. And so far, I think for now, we still need to have a good interaction between these industries and the scientists that can, alert about the complexity of what we know. And that way, working together, we can, I think, move on maybe quicker than we think when we think about computers 20 years ago, and now who would have predicted I mean, wow, the efficiency. So with motivated people and you know, who do not fear the risk level and really want to build something, I'm pretty hopeful we can do something great. So this is the beginning, but it can go very fast. So I think, and it's important. So I think it's very exciting.
All right, thank you, Patrick.
Yeah, thanks. I also very thoroughly enjoyed this today's session. Thanks for the opportunity. I completely agree with my fellow panelists. Space mining or space resource is pivotal to the new space era. I think it's a very important part of it. As a space roboticist, very committed to this kind of new adventure in space and pushing the new frontiers of the human society into space. But of course, as a personal wish, I would like to see more space demonstration missions to help validate, verify the new technologies in maybe first in Earth's orbit and then beyond. I think with those validations in space, it will really pave a more concrete steps for this future, more sustainable space business. So quite look forward to that. I hope Origin Space would be one of the organizers, initiators of doing those demonstration missions, and look forward to some of those future opportunities working together. Thank you.
Thank you so much, Professor Gao. Yeah, Mansu wanna comment?
Yeah, very quickly. I think we're running out of time. I think Origin Space, we are more demonstration missions at lower orbit to get prepared for necessary technologies, maybe maybe crucial or helpful for future mining industry. While doing that, I think we are getting more energy focus and resources for cost-effective precursor missions. So we hope to, have the two roadmaps or two development directions be developed at the same time. That's why we have at the same time we're doing the net capture experiments. So I think we are planning for more missions in both ways. Hopefully we can get the deep space mission as soon as possible while accumulating more experiences at lower orbit. So I think it's a very exciting time. I believe that as keep the right direction and step by step taking, be cautious. I think we are on the way to the final destination. I'm very glad and exciting to have all of you in this panel. Thank you very much.
Good, Mo. Yeah, then I thank again every panelist for this terrific talk and the panel discussion. And thanks for Amara and Dr. Ip to stay with us till this late. We will have two other interesting sessions tomorrow. One is for, hi, Dr. Ip. One is for market and capital, and the other is laws and policy. We'll start at 10 a.m. tomorrow, Beijing time. Welcome to join the, yeah, hi, Amara. Yeah, nice to have you with us. Yeah, hopefully next year we'll have you all in a bigger forum. Hopefully we can see each other again. Well, then see you. Bye bye. 10 a.m.
Bye.
Bye.
tomorrow Beijing time.
Bye.
Bye.
Thank you.